in central Japan near Tokyo.
Hi, this is Justin Crooks, AI7SG. I've been talking a lot about polar modulation and the transmitter on the QRO20, but turns out the receiver is pretty important too, and the parameters that you optimize for in an HF system are not always the same as what you want to optimize for in a VHF, UHF, or microwave system. At the heart of any good receiver is a high dynamic range analog to digital converter. For the QRO20, I selected the AK5534. It's actually a 4-channel ADC, and I actually use all 4 channels, even though it's kind of an IQ mixer design. By using all 4 channels in a special 4:2 mode, I can get 114 dB of signal to noise, which means that you can have a huge in-band blocker without compromising your actual audio quality, which if you've ever been in 20 meters, there's a lot going on, and big blockers show up nearby all the time. So a good receiver design always includes some sort of pre-select filter. You want to remove that out-of-band energy. It may be at lower frequencies, it may be at higher frequencies, but for best performance, you need a bandpass filter. And the next item in the chain is going to be a high IP3 preamplifier. Now, for HF, it's a little bit weird because you've already got this noise floor that's typically, 40 dB above thermal noise. So your calculations when you're optimizing noise figure and linearity kind of flip, where noise figure, as long as you don't completely abuse it, is less important, and linearity is key. So typically, what goes in this position is actually going to be an op-amp. For the QRO20, I selected the LMH6629. It's got less than a nanovolt per root hertz of noise, of voltage noise, which corresponds to something like a 5 dB noise figure, roughly, depending on the circuit. But the important thing is at around 20 meter frequencies, you're looking at about minus 80 dBc for your distortion in like a classic two-tone test. So this op-amp is not going to impact your linearity at all. Next up is the mixer. Now, I don't know if you've heard this, but in school, I heard several times the ideal mixer is a switch, or use a switch to model an ideal mixer. Turns out switches are fast enough nowadays where you can actually directly use a switch as your mixer for HF. However, there is a resistance versus bias voltage for these analog switches. So you want to hunt for a sweet spot where the resistance is as linear as possible. That's going to make this mixer just operate as close to ideal as you could possibly hope for. And finally, after mixing, you're going to want to filter and apply enough gain to match your ADC, considering your noise figure for the band. And what it looks like in the schematics, before this RF in are dual isolation relays separated by a quarter wave pi filter. The reason for that is the relays don't have that great of isolation, and there's up to 400 watts on the other side of that first relay. So you actually need 2 to properly protect your receiver hardware. I also added this ESD protection here, this CD143A, which also doubles if a little bit too much energy sneaks through. It'll offer that protection. For the receive path, it's going to go through this bandpass filter. This down here is actually the VNA path for when you're doing the antenna tuning. The automatic antenna tuner uses the results of the VNA measurement. Then this LMH6629, which I mentioned earlier. Finally, after the preamp, essentially, we're going to go through a quadrature hybrid ring and then into a dual channel switch, which will act as our mixer. This gives us our INQ data, which then gets amplified again using another high linearity op-amp, and then fed to our AK5534 analog to digital converter.